Okay, it's my pleasure to have Yoav Wald here, who got his PhD from Hebrew University with Amir Globerson, right? Yes, I know him. He's done great work. And then was a postdoc at Johns Hopkins. And now is a professor at NYU. And I'm particularly excited for this talk. I think you're going to talk about distribution shift in some sense.
Yeah.
And so an area that I've been working a lot in. So thanks for agreeing to be a part of our workshop, and I'm happy to have you here.
Oh, thanks so much. Thanks for the intro, Adam, and thanks very much for having me. It's a great workshop to be a part of. So I'm interested sort of in the intersection of machine learning and causality and problems in healthcare. And one of the problems where this intersection really comes to life is this problem of learning under spurious correlations, or as Adam mentioned, it's part of the larger field of out-of-distribution generalization. So let's start by just talking about what is out-of-distribution generalization. So in most of machine learning, right, the usual paradigm is that we think of our data as coming sampled from some distribution, p-train, that's our x and y's. And what we assume is that at test time, we'll be tested on data that is sampled from the same distribution, right? So p-train equals p-test. And that's a great assumption because it lets us get some generalization guarantees. So pretty much we can get guarantees about if we are learning from a finite sample and you want to generalize to a new sample, that's great. But it's also not a very good assumption in practice because it often breaks. And it happens in the real world. So this is an example of a problem that happened at the onset of COVID. So many hospitals in the US have risk alert systems for a condition called sepsis. So it's a type of response of the body to an infection that's probably not a bad response. And what happened at COVID is that once COVID patients came into the hospital and other populations came out, the sort of distribution of the population shifted, and that caused these systems to over-alert, and to a point where some hospitals actually had to shut them down. So this is an extreme example of really how data set shift or distribution shift could happen in the real world and damage our models. So now you may say, well, this is yesterday's news. We have the best AI now, and the best AI can generalize out of distribution very well. And it is true that so today's large models can generalize to things that are well outside of their training distribution. So for instance, right, we can generate images of things that are probably sort of, yeah, it's hard to believe that these models saw their training distribution, like these specific images, or these combinations of concepts. So there is a reason to believe that this is true and this probably will go away. But there are also some kind of peculiar behaviors that you could still see in these models. So for instance, here, I asked both Gemini and ChatGPT to create an image of a one-humped camel in the snow. So as you may see, the camel in the image actually has two humps. So there's some kind of a mistake. And OK, so and now I'll ask ChatGPT to ask an image of a one-humped camel in the desert. How many people here think it will succeed? OK, so we have a few. Oh, it's a good mix of yes and no's. And OK, it does succeed, indeed. That's OK, fair enough. And we like to kind of try and interpret how these models quote unquote think. So here, if you go and read about camels, you'll find out that one-humped camels mainly live in deserts where it never snows. But two-humped camels, they actually live in the Gobi Desert, so at least some of them, and the Gobi Desert actually snows quite often. So these are probably observed more in snowy backgrounds. So it seems like maybe there is a type of spurious correlation here. That's been actually failing machine vision systems also 10 years ago. And we're not totally over that hump. So beyond just generating camels, let's look at problems maybe that we care about more. So if you look at X-ray classification, so this table is taken from the latest paper on, one of the latest papers on multimodal Gemini models. So here what model Gemini has are X-rays that were collected from this public data set called Mimic CXR. And what, I see that, the Zoom thing ended? Okay, sorry.
You're using two links for some.
Okay, so we're good?
Yeah, you're good.
Okay. But what they want in this paper is to actually generalize to these two data sets that were kept outside of the distribution, outside of the pre-training data. And if we focus just on one row out of this table, so we see there is a quite a large drop of when we go outside of like the data set of chest X-rays that that wasn't the training data to something that was outside. And actually, it also, like, the model lags behind the state-of-the-art model on that data set. So, yeah.
Quick question. I mean, do you know how they measure if the holdout set has images that are like super close to the images in your training set? Then of course that's also sort of data leakage.
Yeah.
Do you know how they measure,
In this specific paper?
Or in general for X-rays, let's say?
Oh, for X-rays, I don't think there's like a standardized way. So they're just, well, there aren't that many data sets for X-rays. So there's Checkspert. I think these are like the two major ones. Maybe there are some others, but generally, so for X-rays, it's pretty easy to just you either use one or the other if you want to test out of distribution generalization. But in general, I don't think there's a great test. That's like a cool question to think about. But here, so we just see that there is much to be desired, at least from the generalization of these models. And okay, and just one last example, which is the example that will kind of walk us through the rest of the talk. We'll look at this problem of clinical concept extraction. So this is a problem of medical note analysis, medical text. So we'll want to take a medical note and sort of extract all of the medical concepts that appear in it. Okay, so that's going to be the task. And it's sort of like you could boil it down to a binary classification task. And what you get here is that if you take, again, so we're taking a PubMed BERT, so it's kind of like a model pre-trained on a lot of medical text. And then we fine-tune it for the task on this data set mimic-free. So again, sorry, this data set over here. So we see we get great performance on mimic-free. But if we go to a different data set, which is I2B2, this is a medical text analysis challenge, we see there is a large drop of over 20 points in F1 score. Okay, so this problem, we'll see that come up later. So, okay, we see that there's a problem with out-of-distribution generalization, and we kind of need to ask what can be done. So a rather trivial observation that we can make right away is that we can't really do anything without making assumptions on what will happen at test time. Because if at test time I could see either the same distribution or some genie could come and flip my labels totally. So it means that the training data has really no meaning, and if I don't make any assumption on what will happen, I'm bound to fail, right? We don't really have a good solution here. So that means that we need to develop some methods that generalize under assumptions on what will happen at test time. And today I'll talk about assumptions based on the notion of invariance. If you were here for yesterday's talk, there was another talk on invariance. So this will have a bit of a different, twist to it. But invariance mainly is kind of like, it's rooted in causality, and that's sort of like the tie here to causality that I mentioned earlier.
Yoav?
Yeah.
I mean, one thing, if you didn't want to, if you could just go back
Yeah,
to
sure.
the slide. So,
Sure.
like in domain adaptation, as you rightly point out, like if the test distribution has all the labels flipped from the training distribution, then there's nothing you can do.
Yeah.
And you can define a parameter, lambda, that basically measures, what's the error of the best fitting classifier in my training set plus the error of the best fitting classifier in my test distribution. And if that turns out to be, and you can just hope for an you can hope for an algorithm that does well, that achieves error lambda. And if lambda happens to be large, then your classifier is going to have a crappy bound. But if it's small, then you're going to get a classifier that.
Yeah, I agree. So I think like the point here is to say that we can't guarantee anything like better than like non-trivial on an arbitrary distribution. Okay. But also, this was for domain adaptation. I'll actually talk about like a harder problem. It's domain generalization, right? That I don't actually observe like what I will see at test time. Okay. It's a sort of fine. But I agree that this is a good point. So generally, I will go through sort of these 4 parts. Each of them roughly corresponds to a paper, and it's also ordered chronologically. So we'll go from some kind of like pretty old work and work it up. And we'll start with just seeing some basic techniques and talking about what are invariant models, talking about why they don't work, and what can be done to make them work. So it will be sort of like a journey. And I'll start out by just talking about what do you mean by learning invariances, and pretty much what is the problem setting that we'll talk about today. So to start talking about what is the problem setting and what we're going to do, so let's look back at the sort of medical note problem. And we'll just take sort of like a toy example of it. So let's say we have Dr. Alice, and Dr. Alice mainly treats people that have diabetes. And on the other hand, we have Dr. Bob, and Dr. Bob mainly treats people with arthritis. Okay? So Dr. Alice, whenever she sees a male patient, she'll write that she saw a man, while Dr. Bob has a bit of a different style, and whenever he sees a male patient, will write that he saw a gentleman. Okay, so what happened here in this toy example is that the writing style, whether we write man or gentleman, got correlated with the medical condition, whether that's arthritis or diabetes. And that's, of course, a toy example. In the real data set that we work with, there are thousands of caregivers, around 5,000 if I'm not mistaken, and writing style could be things like these expressions, but it could also be things like templates that certain communities of doctors use. So doctors have templates that they use when they're writing text, and these are sort of more common across certain communities and not others, and this also gets correlated with the outcome. So, so to try and formalize this type of shift between writing style and the label, let's look at this sort of framework. So we'll have a set of distributions. We'll denote that by calligraphic P, and pretty much that's a set of distribution that each one of it can be our test distribution. And the thing that will change across these different distributions is a correlation between something we'll call the nuisance, that is Z, okay, which is the writing style, and Y, which is the label. So we'll have this family of distributions, which pretty much tell one story we could think about the world that would generate this type of data. So we'll have this family of distribution that decomposes like that, and the middle factor here changes. And it's nice to visualize that with a graph. So the graph pretty much has one node E, which is the environment, which is our clinician. So the clinicians, we see some of them at training time, but then at test time, we'll see a different clinician that we didn't observe in our data set. And then we have the label, which is the clinical outcome. These both sort of determine, I wouldn't want to say cause, this is fine details of whether that's a causal DAG or not a causal DAG, but never mind. But these two determine pretty much Z, which is the nuisance, and the writing style. So this is sort of, and so this writing style, I'll talk about it in a bit more detail soon. So this is, we actually assume that the learner doesn't observe it, as in we don't have it annotated, right? Because style is this kind of vague notion that we don't have a way to annotate style. Maybe know who's the doctor, but we don't have a way to really give it style as part of the data set. Yeah.
Just intuitively, why would the outcome influence the style? It seems like the clinician would influence the style, but they'll write with the same style regardless of what the outcome is.
So it's sort of, you think about, if you see, well, I think that's, so if you could think about several reasons. So one way to think about it is that if I see, a certain person with diabetes, I will write one thing. If another doctor will see a person with diabetes, then they will write something a bit else.
Isn't that X? Isn't that
yeah, like you could see words like pale, right? So if you have some kind of if you have some kind of a condition, so maybe you have some kind of a symptom, and some doctors will write it in one way, some doctors with another. But yeah, it's a varying thing. I will say so. Another way to so this graph is sort of like I think it's for simplicity. One way we could also look at it and maybe draw a more complicated graph, and which is what actually happens, is that your clinical outcome affects which doctor you get assigned to, and this kind of gets the style and the kind of the correlation flows through that. But yeah, this is sort of like a simplified graph that actually describes many other sort of types of spurious correlations that we can talk about later. But the idea is the same. Okay, great. So, and then the last part of this graph is x, which is the text, which is pretty much generated by the clinical outcome and the writing style. And this is what the learner will observe and will want to classify the clinical outcome from. OK, so once we have this, this data generating process, what's our goal? Our goal is that given an input data set of pretty much the data sets of these x's and y's, which are the notes and their labels, and the doctors who wrote them, so that's the additional data we have. So what we'll want to do is we'll want to learn a model F that is both, it performs well, that is, it classifies the notes correctly, but it also is invariant to changes in the nuisance or in the writing style. So figuratively, that means that if I change man to a gentleman or change anything about writing style, so the output of F should stay the same. Okay, so that's the thing we'll want to achieve. Of course, and then the challenge is that we don't really have Z annotated in our training set because it's this kind of vague notion of writing style that we don't really know how to define. Okay, so how are we going to overcome this challenge? The way we're going to overcome this challenge is by leveraging the variations that we observe between the different caregivers, okay, between the different writing styles we have or the different writers we have in our data set. And this kind of idea of leveraging variations goes back to sort of like ideas in causal inference that were, I guess, like people by Tian and Pearl. And more related is this paper by Jonas Peters and collaborators about invariant causal prediction. Very nice papers if you get a chance to read them. So we'll look at sort of like these methods, like this line of work that takes these methods and tries to kind of take them to the deep learning era and kind of use these ideas in like modern machine learning. And the common approaches to do that is to leverage some things we call statistical dependencies, which I'll tell about a bit more in just 1 second. So let's talk about this common approach of leveraging statistical dependencies. Okay, so the premise, pretty much the overall idea of leveraging statistical dependencies in order to learn invariant models is that we'll learn some kind of a deep representation that will take our high-dimensional data, the text here, okay, and it will extract some kind of a representation, which is low-dimensional, and it should sort of contain all of the features that we want to predict from. And the way it will do that will be by enforcing this type of constraint. So the idea is that we'll say that we want to only keep features whose conditional distribution with the label, okay, so the predictiveness of these features is the same across different environments or different pretty much caregivers, okay? So the idea will only be to keep features whose correlation with the label is stable across different distributions. So this is one type of conditional dependency you may enforce. There are many, many papers that enforce other types of conditional dependencies that you may, or different type of independencies that you may think of, and you could think that maybe they're relevant to your problem. This is just one of them. And you'd usually just kind of craft a loss function. We'll go through an example in just a second that will take maybe Alice's notes and Bob's notes and measure some kind of a discrepancy that will try to kind of enforce this constraint. And the idea is that once this constraint kind of threw out all of the writing style features, we'll just classify from what's left and get a stable and nicely generalizing classifier. So that sounds great. And now what we'll do, we'll just run through one example of such a method. So I guess this is sort of like, it is a math seminar, so I kind of figured we'll dive into the details of deriving one of these methods. And I'll go through one very popular method for that, and we'll we'll also talk about why these methods don't really work in practice later, so take everything with a grain of salt. But the method that is quite popular, it drew a lot of attention in the machine learning literature for quite a while, was IRM, or invariant risk minimization. So the idea in this paper is that we'll have these observed environments. So these are doctors that we see in training time. And here, the representation that we'll learn is just pretty much the output of the model. So in terms of the figures that we saw earlier, so the representation will enforce sort of this independence on is just this output of our classifier. So the probability that we'll look at binary classification. So the output is just the probability that y equals 1. given the note. And then the goal in pretty much is, again, to minimize your training, like the loss over your training data. So here I just kind of wrote a shorthand for the expected loss with respect to a distribution. And the goal is to minimize your loss while enforcing this type of conditional independence constraint, which, if I really spell it out, will turn into this type of equality of expectations. So pretty much for any two doctors in my data set, I will want this type of equality of conditional expectations for every value of the probabilities between 0 and 1. OK, so that's the goal in this, for this method. And the solution they propose is this type of, so we want to go deep learning with this and get a differentiable loss. So what they do is they develop this type of loss function that's seems a bit cryptic. It's the gradient of the loss of the environment with respect to something that multiplied the representation set to 1. OK, so that's a bit of a mouthful. So let's go for a bit of let's take a fun and see how we derive that in a fun few lines. So the derivation of the paper is quite involved. So I'll kind of go into details and I will show like a very quick derivation. So if you read the paper ever, so you'll know that there's like a nice short way to derive this loss. So pretty much that. So if we want this type of constraint, what we can do is actually we'll demand a stronger constraint. So here, what we'll do is we'll demand that if we condition on an output probability of alpha, then we'll want the expected label to be also alpha, and this is a constraint called calibration. So if your model phi of x satisfies this constraint, it means it is calibrated. So what's calibration? Calibration just means that the predicted, that if my model outputs something that says, OK, there is 0.8% that this patient has diabetes, then if I really take all of the patients in the world and see how many of them have diabetes, I'll get 80%. So pretty much it just says that your model needs to output correct uncertainties. So here, the dashed line shows like what should happen when a model is perfectly calibrated. So, this is the notion of calibration. The thing is that we'll want to have that over each and every doctor in our training data set. Okay, we'll want to be calibrated on each one of them. And this is, so my first paper on this type of topic was actually proposing this type of calibration as a type of invariance that lets you throw away spurious correlations. And what we will show in like a few lines of derivation is that this sort of popular method of IRM is a relaxation of this multi-domain calibration loss. So pretty much what you could do is if you write the sort of conditional, the calibration constraint, you could put your alpha into one side and get like, this equality to 0. And you could rewrite the conditional expectation by definition as multiplication of an indicator function on your phi of x. So this is just the definition of conditional expectations. But because this holds for every value of alpha, you could also say that this holds for any composition of a measurable function and f and phi of x, your representation. And then what you get is pretty much, so specifically, it holds for the identity function f, and for the identity function f. And then if you take this thing and you pretty much, and you take the squared loss as your loss, so you'll see that this just boils down to the IRM v1 sort of loss function. It's a fun little observation, and it's related, if you're interested in this type of sort of calibration and relaxations, there is a lot of like theory of CS literature on that for things like low degree multi-calibration, so this paper goes into that if you're interested.
But so there are examples where calibration can hurt accuracy.
Yeah, of course. Yeah. So but the thing is that I think that part of these, right, so part of all of these, I think, methods, right, if you enforce some kind of a conditional dependence, it can definitely hurt your accuracy, right, in some environments.
You're not concerned about that here?
Well, we are concerned, but the thing is, so we'll talk about, what is the guarantees that, well, I'll mention what are the guarantees you actually obtain with this. But for sure, I think one of the potential downfalls of these methods that you get maybe lower accuracy on some distributions, but maybe pretty much ensuring robustness across others. So there is a trade-off. So I agree. And we'll talk about just a second about why these methods fail. I think it's also one of these reasons that they don't really work in practice. So pretty much, okay, so I promised some insights about learning under spurious correlations. So the first insight that apparently you could prove some really nice things about these methods. So in our paper, we kind of took this calibration constraint, and what we've shown is that if you enforce this on enough environments, then what we'll get is we'll really get this invariance to writing style, okay? So, so pretty much on new doctors that we haven't observed. And you'll get the type of guarantee on accuracy that you'll get, and that's related to Adam's question. You'll get sort of like a robustness across the set of all of your doctors, pretty much of the entire distribution. So, and that will be in the sense of min-max optimality. So what you gain is min-max optimality, but you compromise maybe optimality on certain distributions. Okay, so just to kind of give an intuition on how these kind of, so again, going a bit into the math, of how these guarantees come to be. So you could think about taking Gaussian data and linear models. So here, our problem, let's take a toy version of our problem. We'll go back to that later. So here we'll have like two features. One is like sort of like the stable feature, which is whether someone has diabetes or arthritis. And here, like these are the two labels. And here this is right, and on the second feature is the writing style. So, and the two colors are maybe the two different doctors. So you can see that the correlation of X2 changes between these two doctors, while the correlation of this thing stays the same. So what happens is that if you enforce calibration on these type of toy data, you'll get a set of quadratic equations. So these are pretty much ellipsoids, constraints on your weights. And if you take sort of so each of these environments will sort of define an ellipsoid. And if you take the intersection of these ellipsoids, which are the two classifiers, or the classifiers that are calibrated over both doctors, then what you'll see is that they both have sort of like zero weight on W2, which means that they disregard the spurious feature. And that's how you gain these sort of invariants. So really like cool math. It's a nice idea, and so we were able actually to make it also work in practice on some large data sets, and that was also kind of nice. But obviously when you have this kind of elegant idea, there is like a whole literature that gets developed around it. So we were by far not the only ones who were excited by that, and many people kind of developed many types of loss functions, many types of training schemes, and different types of independencies, and all that kind of stuff. And at some point, people had to ask, which they should ask, are these methods effective in practice? And as I kind of hinted to at first, so people actually did this benchmark. So here the columns are just different generalization, out-of-distribution generalization problems. So for instance, generalizing to different styles of images or different locations of images and things like that. And what you could see first, and the rows are each sort of like these methods from the literature that I've kind of mentioned. And what you can see is that there is definitely no clear winner. Maybe in some data sets, some methods have a few percentage advantage over others, but nothing really significant. But the even sort of more shocking, or maybe not shocking, I don't know, it depends on how you view it, insight is if you just take something like empirical risk minimization. So this is the first row here, ERM, which means just minimize your training loss, don't do anything about distribution shift. Then what you'll end up is with sort of like a comparable performance on out-of-distribution generalization. And I will say that perhaps like one of the reasons that they actually got these gaps closed here is that they actually like did a careful implementation of ERM. They did all the standard thing you would do in industry and kind of like augment your data in certain ways. And it turns out to actually sort of close the gap between all of these other methods that people developed. Okay, so that's kind of discouraging. And we ask ourselves, well, why does this happen? Yeah, there's a question there?
Yeah, are these performance like averaged across domains?
No, yeah, I mean, so they have a few variations of these experiments. So this is actually this is a performance on a held out test domain. But you could, yeah, but pretty much then they switch the test domains and average over all of them. So, and you have several variations of this experiment that you could do, yeah. But it's like similar results pretty much in all of them. Okay, so we asked ourselves, okay, why aren't we seeing any more success? And there are several reasons, but here we'll talk about one of them, which are sort of like the problem of these collision of implicit biases and learning invariant models. So, pretty much the second insight we'll see is that it turns out that these invariant learning approaches are just more effective on smaller models rather than the larger models they were motivated by. Or the premise that we set out. And it turns out that the problem is interpolation, is that we're learning with models that can interpolate or perfectly classify our data, and this turns out to be really not sort of like play well with the type of methods that we were developing. So what we started out, the way we started out with this project is we looked at the gaps of going from theory to practice. So the theory we developed and others sort of relies on having these statistical claims on having sort of infinite samples. We think about having infinite data, and we also talked about linear models. Some people maybe didn't talk about linear models, but it doesn't really matter. I mean, generally they were pretty harsh assumptions. But in practice, what happens is that we are learning from a finite sample, and we're also learning with these large, often overparameterized, so we have more parameters than data points, and these models are capable of interpolation. And what happens with interpolation is that once you have this, so you have these many solutions that you need, and you need to choose one of them to minimize your loss. So implicit biases play a role. So this is evident in many works that show that neural networks tend to learn these simple features or formalized by things like the max margin classifier. So neural networks tend to find solutions that maximize the margin of classification, and also the theory that underlies why taking a larger model gives you better test accuracy. So this theory of benign overfitting that's relevant here. So it's obvious that implicit biases play a role once we go to practice, but our theory ignored them, and we kind of set out and thought, okay, maybe we can actually design maybe a type of implicit bias or a loss function that will be compatible with these types of things that we are trying to do of learning these invariant solutions. And actually, we're not the only ones who tried. There are people who kind of claim to getting some marginal improvements. But when we failed to get sort of satisfactory results, we thought, okay, maybe we could actually prove that this is impossible, that there is no such magical implicit bias. So I'll just skip this slide. And what we show in this work is that even for the simplest problem that you could think of, so I'll take pretty much the simplest problem with a spurious correlation that you could think of, and I'll go into the details in a second. We showed it's impossible to learn a model that both interpolates the data, that is, classifies the data perfectly, and is invariant to the spurious feature that you wanted to get rid of. Okay, so there is this type of impossibility result. And the second part of this result is saying that actually you could learn a robust model, but it just has to be like a sort of like method that doesn't interpolate the data. Okay, so that's the catch. And so if that was the premise that we winded up with, we wanted to learn these rich representations that throw out the spurious features, we end up with sort of a revised premise that afterwards people saw like in the literature that actually it gives pretty good performance on several benchmarks. So here what we'll do is we'll actually have two stages that will first learn a representation that is low dimensional but does contain all of the bad features, and then we'll just apply our favorite sort of invariant learning technique on a smaller model on this representation with a fresh data set, and that will avoid sort of like the problems that we talked about earlier. Okay, so this is just a small adjustment, but an important one. And the interesting thing is actually how we get to this conclusion. So I'll go over like a bit of the details of, and this is like another icon of deep dive. So this is a bit of technical details. Feel free to join in a couple of slides if you don't like that kind of stuff. So the way we show it is we take this sort of toy model for learning spurious correlations that's kind of common across the literature. So we have just two features. One is the nuisance, the bad feature, the style. So the style is just represented by this d-dimensional vector. And you have the stable feature, which is another d-dimensional vector. And again, we'll have this two examples. So now the projection of our data point over each of the directions will correspond to either the writing style and or the condition. And our learner will have these two environments. So the set of distributions will be a type of set of distributions that I've talked about before, where there's this shifting correlation between y and z, and theta is the parameter that controls it. But besides these two features, what we'll have is just many dimensions of independent Gaussian noise. Okay, and how many dimensions? More dimensions than data points. So we'll take d to be larger than the number of total data points that the learner sees. And what the learner sees is just pretty much these two data sets taken from the two different doctors. Okay, and once you have this problem, the goal of the learner is to minimize the worst case error over these type of the family of distributions. And you could show pretty easily that if you want to solve that, so any solution will the solution will be pretty much to discard the style feature and just predict from this one. And pretty much any reasonable method that we talked about from the literature, given enough data, should be able to solve this very easily. Okay, and the problem, of course, with implicit bias will be the overparameterization. So what we show is this theorem that says that for any value of gamma, so here gamma is the margin, so pretty much for any value of the margin, and because we show this for any value of the margin, that means for any type of implicit bias you may think of, because any type of interpolation solution, so margin is of course just, right, if we have a separator that interpolates the data, it's just the distance to the closest data point to the boundary. And so for any type of margin, and any robust error, so this is the worst case error that you want to achieve, what we will show is that there exists parameters of these problems where the following three things hold. So one thing is that you could learn a robust classifier in the sense that it gets a robust error that is smaller than epsilon, and this is with the type of algorithm I just showed you. And one trivial observation is that you could actually separate this data set with margin gamma. But the kicker is that if you go ahead and you give an algorithm that does separate the data, a learner that separates the data with margin that's larger than gamma, so it is bound to fail in the sense that it gets a worst case error that is larger than half, so it means it's good as there is some kind of an environment where it's as good as random. Okay, so maybe maybe I'll say like just the proof sketch is pretty much that you could write this type of condition as a sort of fractional linear program, and where the constraints are these separation constraints, and then you take the dual of that and derive some bounds on pretty much the dependence of the learner on your spurious feature, while you show that this algorithm actually has better guarantees. Okay, so sort of in simple terms, what we showed is that there are these sort of like really simple natural overparameterized problems with spurious correlation with just like one spurious feature, the simplest thing you could think, and where any type of invariance criterion that interpolates it will fail. Okay, so so now that seems like maybe we made some progress, right? We have some sort of like a revised version of these methods. Let's go and try them out on the clinical nodes problem that we talked about. Okay, so this is what we did. Here we have, again, these kind of in distribution mimic free and out of distribution I2, B2, which is our the data set that we fail on. And here these bars are different methods. So the leftmost bar is just these empirical risk minimization, pretty much do nothing about distribution shift. We see that one has a large drop. And the rest of the bars are just these different sort of methods from the literature that we tried in our revised fashion. And we see that, okay, at least for 3 of them, you get some kind of an improvement. Maybe for 1 of them, you don't. So maybe it's a good sign. But actually, you know, I mean, if we work that hard only to gain these few points, that's a pretty discouraging sign. So at this point, you may say, oh, maybe this invariance idea is just not really good. You know, maybe we should be looking elsewhere. But you see, I also kind of left space for more bars. So so maybe there is something good to hope for. And indeed, at this point, we kind of asked, okay, can we do better than these sort of methods that we did so far and still leverage invariance in some kind of a way? Okay, so and this is like sort of like the final insight. And this is based on this paper with Amir Feder, Claudia Shi, Suchi Sari, and David Bly, where where the sort of like lesson is sort of like how are we going to use sort of large language models to exploit invariances and actually do better on out-of-distribution generalization. So so the idea is that the methods we saw so far just try to change the loss function, try to kind of change the way we're training our models, but maybe instead we can try and change the training data that we train on and maybe actually create better training data. So the plan would be to take each of these doctors and make them write each other's notes. Okay, so in that way to get a data set that has this invariance imbued in it. Okay, so the plan would be to take Dr. Bob and give him Dr. Alice's notes and ask them, okay, please rewrite these notes in your style. And also do that for Dr. Alice, where we'll give her Dr. Bob's note and ask her to rewrite it in her own style. And you can see that probably the problem with this type of approach is practicality. The doctors have better things to do with their time than to rewrite our notes for our data sets. And we want a way to approximate this. Okay, and what's better, LLMs came around about a year earlier. Why don't we try and leverage these? That sounds like a good idea.
Isn't there also like a huge HIPAA issue there? I mean, how can one doctor look at the patient?
Oh yeah, obviously, yeah. It was more of like just maybe that serves as the motivation for whatever it is. Yeah. So one way you kind of could try and think about doing that is that if you take your favorite LLM and tell it, okay, you're a helpful clinician, and here are some notes that you've written, and you'll give the LLM Alice's notes and Alice's notes as examples. Then you'll give it Dr. Bob's note that you want to rewrite in Alice's style, and then ask it, oh, can you please rewrite that note for me in the style of the other ones that you just mentioned. So, and then you'll get an approximation pretty much of how would the medical note look like had Dr. Alice written it. Okay, so you could see that this is sort of like a causal inference question already, if you're familiar with that. So, but one thing that could go wrong with this approach is that, right, the model could conflate style with medical information, right? That could happen eventually, because if, let's say, all of Alice or many of Alice's patients have high blood pressure, then this might be conflated for the style that she writes, and then you'll get some kind of a mismatch where we actually changed important data in our medical notes. So that's a problem that could happen, and actually does happen. We'll see that in a second. But we could adjust for that. So what we do in our in this work is more of like an empirical work where we try and we say, okay, this is a causal inference question. We're asking, well, how would a note look like had a different doctor written it? So we kind of took inspiration from methods in causal inference to try and do better sort of data augmentation, as we saw earlier. So so we use specifically two methods, matching and difference. So matching would just be that if we have our the node that we want to rewrite, so instead of taking all of Alice's notes, we'll just take we'll take some features that we care about. So here in our experiments we took things like blood pressure, vitals, medications, things like that, and only included patients that match our target patient on these sort of important features that we care about. And if we only include these notes as examples, so eventually what you should get is a correct rewriting of your note. And then another method that we used was difference and difference. I'll gloss over it just to kind of explain what is the idea. So the idea here is that difference and difference is a method that people use in causal inference when you have panel data, so it has data that is spread over time. So here it turns out patients have several notes written on them in the hospitals during the time of their visit, and these are taken by different doctors. And what happens is these natural experiments where some patients actually have their note taken at time t-1 by one doctor and then at time t by different doctors, and we only do classification from the last note, the discharge note. So you could try and use these natural experiments to figure out, okay, what would have happened had this patient gone to the yellow doctor instead of the blue doctor, okay? And the heuristic way to account for this is some kind of like vector algebra that we take the representation of the text and we try and do some kind of like algebra to under some assumptions to approximate what would have happened. Okay, and then what you get, so I added 2 bars here on the right to the plot. So the first bar, the purple one, is this type of augmentation, the naive augmentation I talked about, if you didn't do the 2 things I just mentioned. And then the green bar here is what we get with our sort of like these matching and diff approximations. And these are so here these are 2 different tasks and also 2 different data sets. This is the I2B2 and this is sort of like this was in collaboration with Google, so this was their sort of private data set that we worked on. Okay. So pretty much, the insight pretty much here is that it turns out, maybe if we get creative with the way we use our data, we can actually exploit invariance in the favor of out-of-distribution generalization. Great. So I'll go over like just to the last part to kind of just scope out like some interesting questions that may come up in this sort of space of out-of-distribution generalization, and I'll mention one paper in passing to kind of motivate them. So I kind of really took a sharp focus here on the problem of training invariant models. This is just one problem of many in this scope of out-of-distribution generalization and spurious correlations. And there are many further questions here. So if you could come up with more like the method I showed you was really ad hoc for the problem. Maybe we could come up with more sort of like generalizable techniques and maybe some theory for more general settings. So this is like a question to a crowd here. Would love it if someone did some really nice theory here from that out-of-distribution generalization and variance. And other things that are really interesting in this space is, I talked about this problem where I have environments, I have these doctors. It's unclear in general, like, right, where do these come from? As in, like, I decided that doctors or writing style is a good thing to look at for my problem. Is there like more of like a principled way or maybe other ways to do that? Maybe something other than environments to look at? And also, just how to reason about, okay, what happens at test time? So there are many ways, like many questions around that. So to just give an example of how type of questions that I'm interested in on where do environments come from. So I'll mention this paper that was led by a PhD student at NYU, Arlette Pooley, about pretty much how we can use, what other things we can use besides environments. So as a sort of like a motivating example for that question, we can look at the problem of classifying X-rays. So this is a problem of cardiomegaly detection. So cardiomegaly is a condition of an enlarged heart. So patients with enlarged hearts. And now, right, you may suspect, okay, maybe there is some kind of like a spurious correlation lurking in my data set, but I really don't know what it is. So maybe it's some kind of like the scanner type is getting spuriously correlated, like, people with cardiomegaly get to be scanned in certain types of scanners, or maybe in certain times of days, or maybe some kind of technicians do something different with these people. So it's really hard to come up with a set of environments. And actually, these are all things that were, in the literature, were observed to like spuriously correlate with medical conditions at some point. So perhaps we can use some kind of other additional auxiliary knowledge on our task here. So for instance, here is one thing that we know. We know that if we occlude the heart from the X-ray, then there should be no way of telling whether or maybe, under some assumptions, there should be no way to tell whether the patient actually has an enlarged heart or not. And the idea is, like in this paper, is that maybe we could use these sort of corrupted images where we occlude the part of the image that is meaningful, that contains the information about the label, in order to learn a more robust model. So it turns out that you could use this kind of information about that type of corrupted images. We call these semantic corruptions to learn more robust models. Specifically, the way we do that is we actually try to predict the label from these corrupted images and then use the outputs of the model as inverse weights to the loss in our in a second stage of training. And you could see that here we are almost able to, if we take here is a problem where we know what is a spurious correlation, if we can also almost restore the performance of had we known what is the spurious correlation by these semantic corruptions. In the paper, we formalize this notion and apply it to different types of corruptions and different types of modalities, also in text classification tasks, et cetera, et cetera. So that's just one example of the types of questions I think that are interesting in this space. And of course, sort of the elephant in the room is, okay, what's going on with out-of-distribution generalization when we have large models? Are they generalizing? Are they not? How do we make them better generalized? And there are many sort of, I think, interesting questions here from detecting the spurious correlations to things like in-context learning and different types of generalization. So if you're interested in this type of space, we also had a tutorial at NeurIPS now. And I'm just including this picture to show you that if you come and work on this sort of topic, you'll maybe have a lot of people interested in it. So, but generally, so I think so that's to summarize, there are a lot of interesting questions. And with that, I would just like to thank my collaborators on all of these works. And thanks everyone for your attention. I know we're running late and you all want lunch already. So thanks a lot.
Time for a question.
I guess since no one else is, I'll ask. I'm curious on the data cleaning step that you did kind of halfway through your talk. You mentioned the template where you prompted with 2 examples and then said that the prompt had to contain the key information that you were trying to rewrite. Did you find that it not only did you need that key information in there, but the key information needed to match what the input was? Or could you prompt with different information, even though it still contained it, and you still get the correct output?
Okay. So maybe I'll go back to the slide about that just to. So I think you're talking about like the matching, right?
Yes, this step here. Yeah, on the
exactly.
left. Yeah.
So actually, no, it is really important to sort of like match. So what we do, like we were saying, okay, we want to rewrite this node.
Yes.
This node has low blood pressure, so I'm only going to select as examples these examples that have also low blood pressure. So it is like the matching is super crucial. It's if you just give it something, it's you'll get.
So if you give it high, but you want to rewrite low, it could mess it up.
Yeah, exactly.
Okay.
That's like.
Thank you.
Yeah.
But aren't you then sort of, in some sense, giving the answer of what matters and what doesn't matter? Like what the...
Yeah, I think that's I think causal inference, right? It's so they're nice techniques, but eventually we're kind of like what we're saying is you have to put in knowledge into your system. I have to choose, and I'll be the one like the domain expert. Well, I won't be the domain expert. The other domain experts will tell me what are the important things you want to match for, you want to control for. So this is like you could think about it as like controlling for confounders. So. So someone has to decide what these things are, and also to collect that data. So I agree. Definitely, there is a lot of like extra knowledge that goes into this.
Thank you.
Yeah, thank you.
Okay, let's thank Yoav again.
Thank you.